From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. Beautiful day outside here in Tucson. Well, last class we were talking about holography, and we will continue talking about that today. I've changed the outline a little bit for what I'm going to cover in holography from what I passed out at the beginning of the semester, so I'll just point this out to you now. So this is chapter 17. We had started here with a physical description. We went through a little algebra to show the proof of the reconstruction process. Today we're going to be talking about how do we separate the different orders and what's the smallest reference beam angle we can have to separate orders. We're going to go through some algebra to show where the images are as a function of both how you make the hologram and how you do the reconstruction of the hologram. We're going to talk a little bit about light sources and recording materials. Not all this today, but in this chapter. And then we'll go through some work on volume holograms and coupled wave theory, and we'll talk about applications. And I probably will put the applications actually before we talk to about the volume holograms. But anyway, these are the items that we're talking about in chapter 17, and that's a few more than what I had originally listed in the outline. So we talked last class about kind of physically what happens when we make a hologram. We went through a little algebra showing why we get hologram reconstruction. And I have 3 or 4 pictures here I want to show you today. And some of you have seen these before, but I kind of wanted to go through it here. Just again kind of show what I think is the magic of holography. So let's say we set up here to make some hologram, and there are a lot of different ways of setting up to make the hologram. And this comes from the view graphs that you got at the beginning of the semester. So we're illuminating an object, and it's a diffuse object, so it scatters light all over, and some of that light comes over here to our film or whatever we're using for a recording medium. And part of this light, laser light, reflects off our reference and reference mirror and becomes our reference beam for the interferometer, or for the hologram. So we're interfering the light from the object with this reference beam. And if I take this and look at, now I make the exposure, say I make it on film, and I process the film, develop the film, and let me now look at this plate right here. And I brought a picture of a plate, and I don't know how well this will show up on TV. I guess the answer is not too well. Well, in any case, I'll zoom in, and you can see a little bit there. Get the idea. So this is was a photographic plate. I think it was 4 inches by 5 inches. And this has our recorded hologram on it. And if you look here, you know, you see these fringes. And maybe I should ask you, how many of you have seen this view graph? I've shown it before, not in this class. Have any of you seen this? Because I'm going to ask you some questions in a minute. Okay. Anyway, we look at this, and the first question would be, what is the object that we made the hologram of? And those of you who remember can't answer now. But anyway, the point is that at this stage, you really can't tell, because we see some fringes here, but these are really just Fizeau fringes showing us how flat the plate is, or how non-flat the plate is. Okay, and the real holographic detail is in fringes that are very high spatial frequency. So if we have a large beam angle between the two beams here, the fringes of interest, they're really very high spatial frequency. So we can't just look at the plate and see the fringes. These are just spurious fringes, I would say. So what we're going to do now is to take this and put this under a microscope and look at it in detail. And let's see how this works. Well, can anyone tell me now what the object was for the hologram? Not unless you've heard me give this little talk before, you can't. It's a mess. So this is looking at, high frequency. These are micron type speckles that we're seeing here. And the object was a diffuse beam, a diffuse object, so we had a diffuse beam. Interfere that with a reference beam and we get a mess. We get a speckle pattern. It looks like this. And there's no way that you can just look at this and say, the object was a, you don't know. You can't tell. But the magic here, the real magic, is that what we will do is that we will simply remove the object, illuminate this in the same way it was recorded. And when we look through here, so look through this just like it's a window, and what we will see is a beautiful Swedish music box. Maybe looking at this, you can't tell it's a music box, but it was. And so this this girl and this tree and this chicken or whatever it is, it really was encoded in this mess. And this is a true, I haven't even cheated on this in any way. This was the hologram that was used to produce this. And when you look through here, of course, it's just like looking at this object through a window. And if I move my head around, this tree will move relative to the girl. The chicken will move relative to the girl. And so if I just take this little window and take two pictures of it, one side and one on the other side, what I will see, I see this on, well, yeah, we can get both in there maybe. You see, I see this on one side where the tree is here relative to the girl. Chicken is over there. And here I just moved sideways, looking through the same hologram, but moved the camera sideways, and now the chicken has moved relative to the girl, and the tree has moved relative. And of course, you see the depth. You could focus on the front of this, or you can focus on the back. And I don't know if this is not magic. Well, maybe I shouldn't call it magic, but find the right. Oh, it's underneath here. Nope, I've lost it. Lost my hologram. Here it is. Just you illuminate this with a laser beam and you produce beautiful, beautiful images. So anyway, I think that's kind of neat that it really does work so well. Well, when we produce these images, we actually produce several images. And in the books, sometimes they refer to these as a virtual image and a real image. Of course, the real image may be virtual and the virtual image may be real, so the terminology is not very good, but it's what I would call a primary image and a conjugate image. And there will be also maybe some higher orders. So we get what I'll call a primary image, and we get a conjugate image. And we may get higher orders. So the question that comes first is, I don't want these orders lying on top of one another, because that will produce a very confused image. And so some way I want to separate these orders in space. And the way we do that is to bring in the reference beam at some large angle, or larger angle, and the orders will separate. So at first we'll look at a little bit of math here to see that, and then we'll kind of think physically, what does this mean, and why are the orders, why do the orders separate? And then we're going to go on and calculate where the orders actually exist. So this will be 17.3, which is minimum reference beam angle to separate orders. Okay. Now going back last class, remember we went through this little photographic analysis here, and we ended up by saying what we really, when we think about the recording process, it's the amplitude transmittance versus the exposure that we're really interested in. And we probably have some curve, I don't know what it looks like here, some curve like so. But the point is, what we're going to make use of here is that there's a portion of this curve that is fairly straight line. We could bias the exposure to get up on this portion of the curve, and we typically do that by recording lower contrast fringes, so we have the reference beam somewhat stronger than the object beam. And so if we want to, we could write this as some value here plus a slope, or another beta, minus E minus some bias exposure. And so we are going to assume here that the amplitude transmission is proportional to the exposure. And if we have higher order terms here, we said what that really does is to give us some higher order, higher diffraction orders, and hopefully we're going to separate these in groups. Okay, so how do we separate the primary order from the conjugate order and from the straight through beam? So let's start out here, and I'm going to use, instead of writing all the equations or writing the equations down, I'm going to go back to our view graphs that we had at the beginning of the semester, and you probably don't, most of you probably don't have these with you, but you have them back in your office, so I don't know that you'll need to copy a whole lot of this down. So let's say we're making a hologram here, and we have some object here in space, and I'm going to say that the angles of the light coming from the object range from minus theta naught to plus theta naught. So the range over an angle of 2 theta naught here. Okay? And I'm going to bring in a reference beam here at some angle theta sub r. And our question is, how large does theta sub r have to be to separate the orders? And so if we think here for a second, spatial frequency terms, the spectrum of the object has a width here, 2k sine theta naught. So 2 pi over lambda times 2 sine theta naught. And I've drawn it uniform over that spatial frequency. And I don't know if it's uniform or not. We will assume it is. But what's really going to count is just the spread of spatial frequencies here. Okay? So the angles are plus or minus theta naught. The reference beam is coming in at some angle theta sub r, and so the spatial frequency of that will be k sine theta sub r, 2 pi over lambda times the angle. And the conjugate of the reference beam will be of interest, so I just wrote that down here. That will be minus k sine theta sub r. Okay, so this gives us the spectrum of the object in the reference beam. Okay, so now we are going to make the hologram, and we're going to reconstruct the hologram, and we're going to look at what spatial frequencies are in the hologram transmission function. So we're assuming that we have this linear relationship between the exposing intensity and the amplitude transmission. And so we get a constant here which we don't worry about minus some other constant which we don't worry about, and we get the object times the complex conjugate of the object, the reference plus the reference times the complex conjugate of the reference, plus the object times the complex conjugate of the reference, plus the reference times the complex conjugate of the object. So this is just our normal two-beam interference equation. And now I want to look at the spectrum of this. And so the first one, let's pick the R complex conjugate. Well, R was just a plane wave for my example here. And so it's a delta function here, and so we take this times the complex conjugate and look at the spectrum of that. It's just going to be a spike in the center here. So that's not going to be very interesting. A more interesting term, and a more irritating term maybe, is this O complex conjugate. So if we take the Fourier transform of this, we're going to get the autocorrelation here. We're going to get something that's going to be spread here twice the frequency. So the object is like so, and so when we take the Fourier transform of O complex conjugate here, we're going to get a triangular function, and the real thing of interest is that this will go as twice the width of the object. Okay. Now let's kind of think physically, why is that? And if we go back here and think for a second, we have these rays coming in over some angle like this, and different points on the object will interfere with themselves. So these rays are going to interfere with themselves. So even forget about the reference. We're still going to have these guys interfering with themselves. And the maximum angle between interfering rays then is 2 theta naught. Okay? And so now we get this interference pattern with a highest spatial frequency coming from this maximum angle between the two beams. And so now when we go through the reconstruction process, we're going to be reconstructing these angles, and we're going to have both a plus order and a minus order. So we get, this is just reconstructing the interference of the object with itself. And these are called self-interference terms, or they're called intermodulation terms. Let me write that down. Called self-interference, or some books will call it intermodulation. Okay. So do you see physically why you get this, and do you see why the width is this? You're getting, simple mind thinking about this, you're getting plus orders and minus orders, and so we get twice the width. Okay? Any questions on that? Well, this turns out to be a problem at times. And the way you reduce the amount of light here is that, well, this goes as O complex conjugate, while the orders of interest are going to go like O R complex conjugate. And so if we make the reference beam quite a bit brighter than the object beam, these self-interference terms will become less. Okay. So anyway, that takes care of these two guys right here. Then we have the O R star, and so that's going to be the spectrum in O shifted out here, the spatial frequency by the spatial frequency of the reference beam, and so that would be 2k sine theta naught. And then we're going to get the complex conjugate of that over here. So this is the zero order, the self-interference terms, and what we'll call the primary and the conjugate orders. Now to separate these in space, we have to have that, as this becomes smaller, you want that to not quite touch right here. And so for separation of the orders here, sine of the angle of the reference beam has to be equal to 1, 2, 3 times the sine of theta naught. So theta naught here was, the object beam was plus or minus theta naught. And so the reference beam here has to be 3 times, well, for small angles, this has to be 3 times this right here. Okay. Any questions? Well, let me ask you another question. A question in the back corner.
Well, I didn't completely understand where you came up with that the equation on the top of that page.
Okay. Where did this equation here come from? This right here is just the intensity of the exposing beam. It's just O plus R magnitude squared. Okay, so that's the intensity of the exposing beam. And so we're saying here that we have a photographic process such that the amplitude transmission is, well, some constant which you don't worry about, but it's proportional to the exposing intensity. Beta is something about the film or the recording material, has to do with the slope of that TE curve. Now, if this is not true, then we're going to get some higher order terms here. And so what we're really doing here is we're making sure we separate the first order from the zero order, or what's more important right now, separating the first order from the self-interference terms. And if you make a hologram and you look back at the source in the reconstruction process, you'll see the source and you'll see all this noise around the source, and that's the self-interference terms. Okay. Now let's say we get rid of the self-interference terms. And how do we do that? Well, if the object beam were just a plane wave, we wouldn't have self-interference terms. That would be, or if the object beam were a spherical wave, we wouldn't have self-interference terms. Or if we make the reference beam much stronger than the object beam, the OO star term will be small. So the question I have for you is, what's the smallest, or how large does theta sub r have to be to separate orders if we have no self-interference term? And so now we will reduce theta sub r, so this comes down to right there. And so in that case, theta sub r would be equal to theta naught. And physically, what does that mean? Well, that means that we're bringing this beam down just so we don't quite have parallel beams here. So we don't have closed fringes. Okay. So if we, neglecting self-interference terms, what you want, and I think this is, I'm giving you the answer to one of your homework problems now that I think about it, but anyway. If we don't have self-interference terms, what we want then is just have this angle large enough that we don't have any parallel beams. And again, you know, I like to think of a hologram as being a collection of zone plates. And if we don't have any parallel beams, it means we don't have any closed fringes. We have an off-axis zone plate. Okay. So any question on separation of orders? Well, if you make holograms, you'll find it's very important to separate orders. Otherwise, you get complete messes. And if we go back to Gabor's day, he had trouble separating orders. And I don't think it was because he didn't know how to do it, but I think it probably was because his light source didn't have a lot of coherence. And as we make this angle larger, we're getting more fringes across here, and we need a longer coherence length for the source. And so really the laser is what made it much easier to separate orders. Shall we go on? Okay. So now we have made this hologram, And we're going to go through the reconstruction process. And the question is, where is the image? And so this is going to take us to 17.4, which is called recording and playback geometry. Now, I'm taking this portion out of Goodman's book, and so I don't know that you need to write down the equations. You can get it out of Goodman's book. I noticed late yesterday that Goodman has changed his sign convention from edition 1 to edition 2. So I updated my sign convention at the last minute, which is always a dangerous thing to do. I wanted to make it like his current book as opposed to the previous edition. So I'm going to keep you on your toes. You have to check my sign convention as I go through here today. Make sure I updated everything and not just part of it. Okay. Anyway, we're going to make a hologram here. And say this is Z. And this is X. And this is Y. And we're going to make it using a wavelength lambda 1. And when we reconstruct it, we're going to use a different wavelength. The object source is here someplace. And it's going to have coordinates x0, y0, z0. And so it's back here at distance z0. So that's the object. And we're just going to have a single point for the object, and any real object you have made up of a collection of points, and so we're looking at single points fine. The reference is back here, and this is going to be x sub r, y sub r, z sub r. So this is another point source here, like so. So this is the recording plane right here. I'll switch color for a second. So recording plane, and this is what we would say is our recording geometry. Okay, now we already know, I guess, that if we go through the reconstruction process, keep the wavelength the same, put a reconstructing beam at the location of the original reference, our primary image will appear to be a point source back here where the original object was. And right now, maybe we don't know where the conjugate image is, but we'll calculate that later. But the real question is, what if I move the reconstructing source around here? And what if I change the wavelength? Now where are the images located? So let's now draw our reconstruction system. So again, X, Y, and Z. And so this is a source back here someplace, I don't know where. And we call that X sub P, Y sub P, Z sub P. And this is the reconstruction source. So again, a spherical wave. And our hologram is in this XY plane. And this is our reconstructing geometry. Okay. Well, now we need to go through a little algebra here to determine where the images are going to be. So, get a little encouragement here by drinking a little coffee. So, recording field. So u of xy is equal to AE. Well, we're going to go through here and make a, I mean, this is a spherical wave, and we're going to make a parabolic approximation to the spherical wave, which we've done 100 times this semester. And so this will be what, pi over lambda 1 z sub r times x minus x1 squared plus y minus y1 squared. And so that's our reference beam. Our object beam is, I guess, little a I use. E to the minus I pi over lambda 1 z naught. And then here we have what, x minus x naught squared plus y minus y naught squared. I don't know what I did up, that looks like a 1. This should be what, x sub r and y sub r up here. X naught, y naught here. So we have made a parabolic approximation to the spherical waves, making up the hologram. And so now what we need to do is to take this and square it to get the exposing intensity. And I'm going to get such a mess, I'm going to right now go to a clean sheet of paper here. So I of xy, and again this is all coming out of Goodman's book, so you don't need to copy everything down. So we get an a squared plus little a squared, so these are our so-called self-interference terms, which for spherical waves are pretty simple, plus capital A, little a complex conjugate, e to the minus I pi over lambda 1, x minus x sub r squared plus y minus y sub r squared divided by z sub r plus x minus x naught squared plus y minus y naught squared over z naught. So this is all, I mean, this is all in the exponent here, okay? And then the other term, what's that?
In the bracket, there's a conjugate.
Okay, let's see. Well, the A sign will remain the same, and the other one, you're right, there's a minus sign here, right? No, there's not. There's a, no. That's a plus sign because it's going to be a conjugate of this right here. So that should still be plus. Oh, yes. Okay. You people, I warned you that I changed the sign convention last night, and I see one I didn't get it right then. So that is minus sign. Right, so minus sign because we have another minus sign there. Good. You're on your toes. Okay. So the next one here will be a complex conjugate, little a, e to the I pi over lambda 1. Now, have you tell me what the signs are here. I'm getting nervous. X minus x sub r squared plus y minus y sub r squared over z sub r. And then we have another one here. I'll leave a sign blank for a second. X minus x naught squared plus y minus y naught squared over z naught. Now, is there a brave person here who will tell me what the signs are? Yeah, this one is minus here, right? So this will be the complex conjugate of what we have up here. And so one of these terms, I don't know which one, I'll pick the first one, I guess. Doesn't matter which I call it. But one of these will be, well, I'm going to call that term number 3, which that makes sense. But then that's going to be what I'm going to call the conjugate term. And this other term down here will be term number 4. And if I call that the conjugate term, then this will be the primary term, or primary image. Okay. Okay, so we have, we have this self-interference terms, which we're not going to worry about right now. And we have the primary image and the conjugate image here. We're going to worry about them. Next thing is we're going to assume a linear process. So we're going to assume amplitude transmittance. Proportional to exposure. Okay. And so the terms of interest here are T3, which are beta prime times term number 3, and T4, which is beta prime times term number 4. Okay, so now we're going to take this hologram, process it so we get this linear relationship between amplitude transmittance and exposure, and we're going to illuminate the hologram with a spherical wave. So we're going to illuminate with a spherical wave, and again we're going to make the parabolic approximation to the spherical wave. So we'll say this is u sub p is equal to some number b, e to the minus I pi over lambda 2 z sub p. X minus x sub p squared plus y minus y sub p squared. Okay. And then the two terms will be of interest will be u3 of xy, which is t3 times this u sub p, the reconstructing beam, and then u4 of xy, which will be t4 u sub p of x and y. So we're going to take this spherical beam and multiply it times this mess I have on this page right here. And what we want to do is to determine the z-coordinate as well as the xy positions. So we want to determine the z and the xy. So the terms in x squared plus y squared will give the z-coordinate of the image. Okay. And the terms in x and y give these off-axis position. Okay? Everyone with me? So. I may have. I'm leaving that possibility here that the wavelength can be different. Any other questions? Okay, so now, really of these, the more interesting one is the first one, so let's look at that first. Let's look at the x squared plus y squared term. So we're going to get an equation here, and then we're going to scratch our heads a little bit and think about it. What does it mean? Okay. So we get an equation here that goes as e to the I pi. So it's just combining, doing this multiplication and combining terms. We're going to get something that goes e to the I pi times a minus or a plus 1 over z1 z sub r, and a plus or a minus. So if this one is minus, this one is plus. 1 over, well, I misspoke here. This is lambda 1 z sub r. Lambda 1 z sub r. And this is going to be lambda 1 z naught. Plus 1 over lambda 2 z sub p times x squared plus y squared. Okay. So I think the top set of signs for U3, which is what we call the conjugate image. And the bottom set of signs for U4, which is what we call the primary image. Okay, so now we have this. What we want to do is to compare this with a spherical wave diverging from a point, a distance z sub I to the left of the hologram. So I'll write that down. Compare with spherical wave diverging from a point, a distance z sub I to the left of the hologram. And with our sign convention, if we're to the left of the hologram, this would actually be a negative number, but let's call it z sub I. And so in that case, we would have something that goes as e to the minus I pi over lambda 2 z sub I x squared plus y squared. And I'll just say it again. It's z sub I negative virtual image. So it is to the left of the hologram. Z sub I positive, it would be a real image. Okay, so we're taking this expression right here, and we're comparing it to this previous expression right here. And we end up with a result that z sub I is given by, well, 1 over z sub I is 1 over z sub p plus or minus lambda 2 over lambda 1 z sub r minus or plus lambda 2 over lambda 1 z naught. Draw a box around that. I don't expect you to memorize that equation at all. And if we go back and we think about zone plates, This is it's the same result as what we got for zone plates. It's the same, hologram is nothing but a collection of zone plates. Okay, so we have this equation, and what I want to do now is to look at a couple of cases here. And the first case is if lambda 2 is lambda 1. So what if we're going to use the same wavelength in a reconstruction as we used in the making of the hologram. And furthermore, z sub p is z sub r. So the reconstructing source, z position of that, is the same as the original reference beam location. And so for one image, z sub I is going to be equal to z naught. Okay, so these would cancel, and we would have the object is the image is at the same location as the original object, and that's our primary image, and I mean that's no surprise, that's what we expected. For the second image, what we'll call the conjugate image, well, now 1 over z sub I is going to be 2 over z sub r minus 1 over z naught. Okay, so it's located someplace else. Well, if we further make a special case that z sub r is equal to infinity, now and also z sub p is equal to z sub r, which is what we said before. But if this is at infinity here, then z sub I is equal to minus z naught. Okay. So if I make a hologram like the following, make a hologram here, plane reference beam, and let's say the object is here. When we reconstruct, we're going to get one image there, and the other image is going to be minus that, so the other image will be over here. Okay? So magnitude anyway is the same. Okay? So that would be the two. It's supposed to be same distances here and same size actually. Okay? Now you might say, how did I know it was here and not up there or something? I mean, later we'll drive an equation for that, but we can just think again physically. Beam comes in. We're going to produce an order that appears to be coming from there. Zero order goes straight through. And the minus 1 order will leave on the other side of this at the same angle. So it will come down here. These angles are supposed to be the same. Okay. So everyone sees this, that when the reference beam was at infinity, and we reconstruct with the reference beam at infinity, or reconstructing beam at infinity, one object, one image is where the original object was, and the other image is going to be on the opposite side of the hologram, same distance. Okay? Now this conjugate image is a strange creature here, and let's look at that a little bit more. So we had for the conjugate image, just copying this down here from above, 1 over z sub I is 2 over z sub r minus 1 over z naught. And this will be a real image if z sub r is greater than 2 z naught, and a virtual image if z sub r is less than 2 z naught. Okay. And we could take derivatives here if we want to and say d z sub I over z sub I squared is minus dz naught over z naught squared, or dz sub I is minus z sub I squared over z naught squared dz naught. And this image is what we call pseudoscopic. And so if we think here for a second, let's say we made this hologram and we had an object that looked like this. For simplicity, I'm going to make it with a plane wave, but it doesn't have to be. So that's the object. And one of the images looks like that. The other image is on the opposite side, and the distance on the opposite side is the same as the distance to the original object. So this point would be there. This point would be here. That point would be there. So on. So the thing is, if this is, and we're looking in this way, if this is convex, this image here, the conjugate image, is concave. And that's what we mean by pseudoscopic. So if I made a hologram of a basketball, okay, we would end up with a concave basketball, which is hard to buy, but we would have one. Okay. I mean, it's weird. Some of you have made you've made some holograms, and I don't know. Have you ever looked at this conjugate image? I mean, it can be strange. You look in there, and it messes up your eyes because things that are supposed to be sticking out are recessed in, and it's confusing. Okay. Kind of neat. I always figured there's money to be made on this conjugate image, but I never figured out how to do it. I don't know. Maybe you can figure out a way to do it. It's so strange. And it's nice that it's forming this real image here too. That somehow this is a nice kind of nice imaging system. Must be some use for that. Okay. Another case I like to look at. This is a neat one here. This is getting pretty close to one of your homework problems, I'm afraid. Let z sub r equals z naught. And so we're saying that the reference beam, the z position of the reference and the z position of the object are equal. And we'll write down some equations first, and then we want to think about physically what's happening here. So if go back to our equations on the previous page, 1 over z sub I is 1 over z sub p plus or minus lambda 2 over lambda 1 z sub r minus or plus lambda 2 over lambda 1 z naught. And the interesting thing is that 1 over z sub I, so now we're going to let z sub r equal z naught. And so 1 over z sub I, well, this cancels out. Independent of the wavelength, it cancels out. That's neat. It's 1 over z sub p for both primary and conjugate image. That's kind of interesting. So let's make this hologram here. Well, let's do this. Let's say this is the one of the points. This is say the reference point. Let's say the object is something up here. Okay. And now, so this is making a hologram. And now when we reconstruct the hologram, and I don't care where the reconstructing source is, I bring it in closer, we're going to get one image here, and the other image will be here. Same plane. And if this is point A, is point A here or here? Any brave person want to volunteer an answer to that? Well, the farther we are from that off-axis, the larger the angle. And so the larger diffraction angle. So if that's point A would be there too. If that's point B would be there, point B would be there. Okay? And so, and as we take this reconstructing source and move it back and forth, these images are going to move back and forth in the same plane. I think you can probably believe they're going to get larger as we move further away, but they're going to be always in the same plane as the source. Now, I mean, the equations predict that, but forget about the equations for a second. Let's see if we can understand why that would be true. And this, I'm really answering a homework problem. I shouldn't do this, but I will. If we have a source here and another source in the same plane, what do the fringes look like here? This is your homework problem. Has anyone worked the homework problem yet? I figured you probably would have done it last week. I don't know if I ever told you the story about this when I took a course from Rudolph Kingslake 100 years ago in Rochester. We used to have one course a week, and what he did was homework problem a week. One lecture a week, one homework problem due a week. So the first day of class, he handed out the homework problems for the whole semester. And you're supposed to work one a week. Well, I went to a second class, and the guy next to me said, "Boy, this homework assignment was really a killer." Well, you can guess what he did. He worked all the problems for the whole semester. So I was impressed with him. Okay, so you haven't worked the homework problem. But if we just think here for a second, these 2 points are in the same plane. And so the fringes here are essentially straight fringes. Straight fringes diffract beams sideways, but there's no power. In order to get power, you have to have these curved fringes. There are no curved fringes here, so there's no power in this hologram. And that's what this is saying here, that the reconstructing image is in the same plane as the reconstructing source, because there's no power in the hologram. The fringes are straight. Okay? So let me ask you another question. Let's change this a little bit. And let's say we do the following. We have a source there, and we're going to put an object here, same plane, but let me put another object here. Okay? And now we're going to reconstruct this. In the reconstructing process, put a source here. And so let's see, that's going to reconstruct this guy here and the conjugate image there. This guy is going to be reconstructed here. And how about on the conjugate side? Is that going to be Closer to the, is it going to be this side or this side? Take a sip of coffee while you think about it. Any brave volunteer? What, ahead? Maybe we should vote. Democratic process again? So, say closer to hologram, farther away. How many say closer? One brave person. 2, 3, 4. Oh, getting more brave as time goes on. How many say farther away? 1, 2, 3, 4, 5, 6. And everyone else, same plane. Well, it's farther away. Okay. I mean, it's a conjugate. It's a minus order. So it's going to be farther away. But this thing is really neat. This is cool, what happens. I made a hologram like this when I was a graduate student. I made one, I had a picture of the library of the University of Rochester, and I had a pencil in front of this picture, okay? So here's the picture of the library, and here's my pencil. When I reconstructed it, I saw the picture of the library. Well, I saw the picture of the library and the pencil. Here I saw the picture of the library, and the pencil is behind it. But the thing it is, and you can look through here with your 2 eyes, you can see it's behind it. There's no doubt about it. But it's blocking what's in front of it. Okay, so it's behind it, but it blocks what's in front of it. Okay, I mean, you don't think that's, I mean, you can see your physical way it's doing. This is in front, and so at certain locations, I mean, the light from back here is just not getting to the hologram, and so it's not going to be in the reconstruction. So you have this thing behind it, but it blocks what's in front of it. It's really a cool, one of the coolest holograms ever made. Okay, pretty neat. Okay, any questions? So we spent a fair amount of time looking at the z coordinates. We want to say a little bit about the xy coordinates, although it's not, in my opinion, not nearly as interesting. Question?
Process. What about if the light you use to illuminate the hologram is not the same as the reference beam? What would happen for the image?
You mean a different wavelength?
Yeah, used to reconstruct the hologram.
Yeah, okay, so now we're saying we reconstruct the hologram with a different wavelength. And it shifts the position of the image we had from back here. In general, it will shift the position of the image. And it's just like a zone plate. Let's see, with a zone plate, if we go to shorter wavelengths, we get a focal length that is, that was an exam question. Does anyone remember? Becomes what, longer? Longer. And so in general, the location of the image and the size of the image will change. The neat thing here about this case where we have no power in the hologram is that these wavelength terms cancel out. And so as far as the z position goes, these are in the same location. We may have some problems with xy, but the z would be the same because there's no power in the hologram. So the position and size will change if you change the wavelength. In fact, you have rather severe chromatic aberrations with holograms. Well, let's look at the xy coordinates of the image. And again, this is in Goodman. And if we go through here, what we want to do is to keep track of the xy terms, and we want to compare the results with, well, we have this spherical wave off-axis position. And so if we were to expand the phase factor of that, we would want to compare this with e to the minus I, 2 pi, over lambda 2 z sub I, x sub I, x plus y sub I, y. So that's just taking our taking a spherical wave and looking only at the xy terms, not the x squared, y squared terms. And so the two terms of interest, if we go back and look at the making of the hologram, the reconstruction process, the two terms of interest are e to the minus I 2 pi. And I'll just copy these down here, hoping we have the signs right. Minus or plus x naught over lambda 1 z naught, plus or minus x sub r over lambda 1 z sub r, plus x sub p over lambda 2 z sub p, all this times x. And still in the exponent here, we get a plus and then a minus or plus y naught over lambda 1 z naught, plus or minus y sub r lambda 1, this is plus or minus y sub r over lambda 1 z sub r, plus y sub p over lambda 2 z sub p times y. And now if we solve for the x terms and y terms, let's see, therefore x sub I and minus or plus, and please no one memorize these, minus or plus lambda 2 over lambda 1, z sub I over z naught, y naught, plus or minus lambda 2 over lambda 1, z sub I over z sub r, x sub r, plus z sub I over z sub p, x sub p. And we have a very similar thing for y sub I, and I'll write it down. Oh, yeah, I think you caught me here. This right here is an x naught. Thank you. I mean, these are all x's. X naught, x sub r, x sub p. And now we'll get the y's down here. So that's minus or plus lambda 2 over lambda 1 z sub I over z naught, y naught, plus or minus lambda 2 over lambda 1 z sub I over z sub r, x sub r, excuse me, y sub r, plus z sub I over z sub p, y sub p. And, well, let's see, we could go through here and solve for the magnification. And I'm going to skip a couple of lines here. That if we find here magnification is delta x sub I over delta x naught, which is delta y sub I over delta y naught. That will turn out to be, so the magnification is going to go as lambda 2 over lambda 1, z sub I over z naught. So the ratio of the wavelengths to the image position to the original object position here. And Let's see, what else might we write here? It's one interesting case, a kind of interesting case here, that if z sub r is z sub p is infinity, so I have a plane wave, then the magnification here is going to turn out to be equal to 1. Well, let's see here. Regardless of lambda, the ratio of the wavelengths. Okay. So if we reconstruct with a, it will turn out if we reconstruct, we make the hologram with a plane wave, we reconstruct with a plane wave, the magnification is 1 independent of the wavelength. And I think there's some other conditions, special conditions we could look at, but I think I will not bother to look at them here. Again, this is all given in Goodman's book if you want to go back and check it. But the way of thinking about this is, it's a zone plate, it's an off-axis zone plate, it behaves just like a zone plate, and images are given the same location as the images of a zone plate. Now we went through here, we made the parabolic approximation to the spherical wave. We didn't keep any of the higher order terms. What would you guess we would have found out if we had kept the higher order terms? Other than that we would have spent about 3 more lectures going through the algebra. What would we have learned? The aberrations. This was looking at where the image is, and by throwing away the higher order terms, we're not saying anything about the aberrations. And so if you keep the higher order terms, you'll derive the equations for the aberrations. And it's kind of interesting. The aberrations turn out to be the same as what you have for lenses. Same form, you have your coma, your astigmatism, your spherical, and so on. And so when you make a hologram at one particular conjugate, set of conjugates, and a wavelength, and you reconstruct at different wavelengths or different conjugates, you will get the normal aberrations that you get from lenses. You do get severe chromatic aberrations, I might add, though, much worse than what you see from normal lenses. Any questions on this? Okay. Well, I think the idea today, that the 2 topics we covered were how do we get rid of the, how do we separate the different orders, and where are the images located, are kind of important items to know in holography. Next class we'll come back here and we'll talk about light sources and recording materials and applications. So I'll see you next Tuesday morning.